Okay, let's continue our discussion of Chapter 3 by talking about components that you might encounter in free body diagrams. And let's start with a simple case of a weight hanging from a cable to refresh our memories on how to draw a free body diagram. So let's first draw the space diagram. And the space diagram is usually what's going to be given to you in a problem. So I'm going to draw a ceiling here. Here's my cable, and my weight is hanging off of the cable like this. Let me just do a little fill so that just make it look nice. And here's our weight W. Okay, so this diagram just shows us how our object is existing in space. It doesn't really tell us what forces are acting on it just yet. I mean, you probably can get it in your head with this simple example, but what we really need to do, especially when we get to more complicated systems, is we need to draw a free body diagram, right? And the free body diagram is just such a useful tool. Once you have a nice free body diagram, the rest of this is so easy. So drawing the free body diagram can be tricky, but in this case, I think you guys are smart. You can get it. So we've got a weight that's acting down, right? We'll call that W. And then we've got the tension of the rope that's pulling this upwards. Right, so we've seen this before, but here's our free body diagram. Now, the next part requires us to make a couple additional assumptions, and that is we're going to make a simplified free body diagram where we're going to idealize this weight as a particle, because we don't really care about the shape of this weight, right? The fact that it's kind of trapezoidal. If we're just interested in the tension in the cable, then the shape of this weight really doesn't matter to us. So we can simplify and call that weight just this particle, which I'm going to draw as a little dot. And all of our forces are going through that particle, right? And even in our not simplified free body diagram, we can see that the forces, the T and the W, they do intersect at this point, right? I mean, they share the entire line, but if we pick this point somewhere, around the center, then both of the forces do go through that point. So, all right, here's our simplified free body diagram. And now with this, it's really easy for us to apply equilibrium to work out what the tension is in the rope. So if I write my equilibrium equation, remember equilibrium means sum of forces equals 0. Now I'm going to establish my coordinate system here and say that x is horizontal and y is vertical. So the only equilibrium equation that applies for this simple case is equilibrium in the y direction, right? Both forces are acting in that direction. So that means that my tension, T, minus my weight, W, has to be equal to 0. And if I rewrite that, it just means that the tension is the negative of the weight. So all this is telling us is that tension is equal and opposite direction of our weight. And we could also do this using our Cartesian coordinates, right? So if I wrote my tension in Cartesian coordinates, it would be 0 I hat plus T j hat. And the W would be 0 I hat minus W j hat. And then if we added up our J components or our Y components, we would get the exact same equation that we got here. So this weight is an example of a two-force body. And there are many different types of two-force bodies, but all it really means is that there's two forces acting on the body. Pretty easy, right? So with a two-force body, the things that you have to keep in mind are that those two forces they must be acting on the same line of action. So remember, line of action is the direction, not exactly the direction, but it's the line that goes through our vector. So in this example, our line of action is this vertical line running up and down. And both of our vectors, t and w, are on that same line. They also must be of the same magnitude, right? Because we must have forces that are equal and opposite to cancel out when we apply equilibrium. And so the magnitude of our tension has to be the same as the magnitude of our weight. And that's something that probably you have worked out intuitively, but it's helpful to write this out for when we get to more complicated examples. And then the two forces must also be pointing in opposite directions, right, in order to cancel each other out. Okay, so keep that in mind. And here's some examples of a few different two-force bodies. So of course, on the left here is the one that we just went through. Here is a two-force member. So it's a beam with just two forces acting at these pin joints. And we've got a chain that is being pulled on in opposite directions. And then we've got this kind of L-shaped bracket that has pin joints on either end, and that's being pulled on by this vector D and D prime. So in each case, we have two vectors that are equal in magnitude, opposite in direction, and acting on the same line of action. Now, you'll notice that, for example, these two forces are pointing towards each other, and that means that the object is in compression, right? We're compressing the material between those two vectors, B and B prime. And then for the chain, the two vectors are pointing away from each other, so this chain is in tension. Right? We're pulling it, we're applying a tensile load. Now, some two-force bodies can only support one or the other. They can only be in compression, they can only be in tension. Now, an example that we're going to see a lot in this class is cables, which is very similar to chains. And those can only support tension, right? I don't know if you've heard the old adage, you can't push a rope, but it's true. You cannot push a rope. Cables can only support tension. So, another thing to keep in mind when we see components in this class. We're going to talk about cables and we're going to talk about pulleys. So pulleys, which we've already seen, but we can assume that they are frictionless. We're not going to cover friction until pretty late in this course, so for most of the time we will not be dealing with friction at all. So we can assume that any pulley you see is going to be frictionless, and what that means is that the tension in one side of the pulley is equal to the tension in the other side. Or in other words, the tension in the cable is constant along the length. Right, so it may change direction when it goes through the pulley, but the magnitude of the tension in the cable is going to be the same on either side. And let's do an example to really see that. So here in this example, we have a pulley with a mass hanging on it. This is mass M. And our pulley D here is resting on this cable, the ABC cable, and there's another cable, this DE, that's being pulled on with force P. And the question here is, what is the tension in cable A, B, C, and DE to keep the system in equilibrium? There's that word, equilibrium. Sum of forces equals to 0, right? First thing you should think when you see that word. Okay, so first let's deal with something that we covered in chapter 1, right? We've got this mass here that is given to us in pounds mass. So make sure that whenever you see this, that you remember this is a mass, this is not a weight. Now we're going to find that it works out actually to 100-pound force, but you need to think through why that is. So remember that 1 pound force is equal to 32.2 pounds mass times feet per second squared. So I'm basically taking 1 pound mass times 32.2 feet per second squared, that's acceleration of gravity. That's equal to 1 pound force. So if I divide 100 by 32.2, 100 divided by 32.2, what I'm going to get is 3.11 slugs. And then I need to multiply that by the acceleration of gravity, which is 32.2. So I get that my weight is 100 pounds force. Okay, so it worked out to be the same magnitude, but remember that you do have to do this conversion, because if there's ever a situation where you're given pounds mass and the acceleration is something other than just the acceleration of gravity, or you have, your object is on a different planet, so the acceleration of gravity is different, or you're very high or very low, in any of those cases, then your weight will not work out to be the exact same number. So just a little aside from chapter 1 there. All right, now let's get back to the problem at hand, which is finding the tension in these cables. So the first thing I want to do is I'm going to draw a simplified free body diagram. So here's my point D, which is the point on this pulley, and I'm going to idealize all my forces, all my tensions, and my applied force P as going through this point D, right? So my mass and my force P is very easy to see that that's exactly where they are applied. These forces from the tension we are also going to idealize as actually going through this point D here. And that's because this distance is very small and the moments that would be applied would actually cancel, but let's for now just think about it as this is a very small distance. So we're going to idealize these tensions as taking place up here. Okay, so let's draw those forces. We've got our tension, tension T right there. And tension T over here too, right? So remember, tension is the same on either side of our pulley. And then we've got our applied load P right there. And our weight acting downwards, which we just solved for, as being 100 pounds. Okay, that's our simplified free body diagram. And now we just need to break our vectors up into components so that we can apply equilibrium in each direction, right? So to do that, I'm gonna just come back up here and do a little bit of trig to work out some of these angles. So first of all, I'd like to get this angle here because that will tell me the angle that the tension on this side of the pulley is acting, right? So this angle is going to be the tangent inverse of opposite, 3 feet, over adjacent, 6 feet. So you guys see that, right? That I'm forming a triangle here that is this 3 feet by 6 feet along the length. And so when I plug that into my calculator, I get 26.6 degrees here. All right, and next I would like to get the angle that the force vectors P and T make on this other side. So that's this angle. And again, I'm gonna form a triangle. This time my triangle is this 3 feet along the horizontal distance here and still 3 feet vertically here, right? So my angle is going to be the tangent inverse of 3 feet over 3 feet. And that gives me, that's just 45 degrees, right? Makes sense? Okay, so there's our angles. And now we can break down our force vectors into their individual components. So let me actually just make this bigger so that we can see what we're doing here. And I'm gonna draw each of the components. So, well, first let me draw our horizontal line. So this is our x-axis. Okay, and my angles, we had 45 degrees here, and we had 26.6 degrees here. So I could have drawn that at a steeper angle, but oh well, it still will serve our purposes. So drawing the components of T on the right hand side, I get tx is this vector, and ty is going to be acting up like this, right? So I'm forming a rectangle. Not much of a rectangle, is it? Let's do it like this. So I'm forming a rectangle here with my t vector, and the x component is going to be t cosine 45 degrees, and the y component is going to be t sine 45 degrees. Okay, and then we can do the same thing for p. So I'm going to have a vector along the y-axis and a vector along the x-axis. The x-axis one is p cosine 45 degrees, and the y-axis one is p sine 45 degrees. Okay, again, I'm just making this rectangle, right? Now w, that's already just in the y direction, so we don't need to break that one up. And then t, I've got a component that's pointing in the negative x direction, and the magnitude of that is t cosine 26.6 degrees. And then I've got a y component that's also acting up, and this one is t times the sine of 26.6 degrees. Okay, so once you get through with that, the rest of this is easy, okay? Setting this up, the free body diagram and the angles and all the components, that's the hard part. Once you've got that done, the rest of this is easy. So all we got to do now is write our equilibrium equations. So sum of forces equals to 0, right? And I'm going to do that in the x and in the y direction. For the x direction, sum of forces in the x equals to 0. So let's sum up all the force components I've got that are acting along the x-axis. Okay, I've got t cosine 45 degrees plus p cosine 45 degrees and minus t cosine 26.6 degrees, right? And I can plug some of this stuff into my calculator. I get that this is t times 0.707 plus p times 0.707 minus t times 0.894. So if I just combine like terms, I get 0.707 p minus 0.187 t is equal to 0. That's my first equilibrium equation. So let's hang on to that and then write our equilibrium equation in the y direction. And that is going to be equal to the sum of all of these components that are acting in the y, right? And then minus our weight. So let's write all these out. We've got t sine 45 degrees plus p sine 45 degrees plus t sine 26.6 degrees, and then minus our weight of 100 pounds. So again, just plugging stuff into the calculator, I get t times 0.707 plus p times 0.707 plus t times 0.448 minus 100. Okay, so 100 equals, I'm just moving this 100 over to the other side. So 100 equals 1.155 t. That's just 0.707 plus 0.448 plus 0.707 p. Okay, so here's my second equation. Now I've got two equations, right? And I have two unknowns, that's P and T. So I can solve this system of equations. And because I notice that I have the same coefficients for P in both equations, the way that I'm going to do it is I'm going to take equation 2 and I'm going to subtract equation 1. Now you can just solve, if you don't want to do that, you could just solve this equation for P, plug P into this equation, and then solve it for T, just as we've done in previous examples, but I just wanted to show you another trick that you can use to save a little bit of time. So if I take equation 2 and I subtract equation 1, I get 100 equals 1.155 minus negative 0.187. So these are just the coefficients in front of T, and then I get plus 0.707 minus 0.707 P, right? And then this equals 0. So that's what I was seeing when I first set up this equation, is that this and this, if I subtract this from this, that this would go to 0. Okay, so then I have 100 equals 1.342 times T. So T is equal to 100 divided by 1.342. That's 74.5 pounds. Okay, almost done. Now we need to plug this back in to our first equation. We could plug it into the second one too. I'm going to use the first one though. And so we find that we have 0 equals to 0.707 P minus 0.187 times what we just got for T, which was 74.5 pounds. Then just moving this stuff over to this side of the equation, I get 0.707 P equals 13.93 pounds. And so P is equal to 19.7. Okay, so those are the forces that we need in order to have equilibrium of our system of pulleys up here, or our system of one pulley with a couple cables. So there's an example using pulleys and the assumption that they're frictionless, so we have the same tension on either side of the pulley. And next time we get together on Thursday, we will talk about some other components like springs and wheels, to talk about how we can interpret those for free body diagrams. So see you then.